The Atlantic, February 1943. Depth charges tumble from HMS Harvester's stern racks, trailing white plumes as they sink into black water. The U-boat commander counts 5 seconds, 10, 15. He orders hard rudder. The boat heels over, 20 seconds. The explosions arrive, distant thumps that rattle pipe fittings but nothing more. The submarine has slipped away again. For the destroyer crew above, it's the same maddening pattern they've endured for 3 years of convoy duty. Drop charges where the submarine was. Watch it escape to where it is now. Repeat until the U-boat crew laughs or your magazine runs empty. But 140 miles northwest, aboard HMS Vanessa, something different is happening. The submarine contact is solid, 800 yards ahead. The captain doesn't turn his ship. He doesn't race to position his stern over the target. Instead, he maintains course, maintains speed. At 250 yards, he gives a single word: fire. 24 projectiles arch forward from the bow, clustering in a tight pattern ahead of the ship. They enter the water without fanfare, without the theatrical splash of depth charges. Beneath the surface, U-432's hydrophone operator hears them coming, a sound like hailstones getting closer. He has 4 seconds to understand what's happening. 4 seconds before contact-fused bombs strike the pressure hull simultaneously. The forward torpedo room floods in 11 seconds, the control room in 18. 73 seconds after the first impact, U-432 is a flooded metal coffin settling onto the seabed at 187 meters, carrying 26 men who never had time to scream. The weapon that killed them had been operational for exactly 4 months. The Germans didn't know it existed. When they finally recovered fragments from survivors' accounts, Kriegsmarine analysts refused to believe the reports. A forward-throwing mortar. Impossible. The recoil would tear a ship's bow apart. Yet this impossible weapon would sink more U-boats than any other Allied technology. Its name: Hedgehog. If you're fascinated by the engineering battles that decided World War II, subscribe now. We're diving deep into the weapon that turned the tide of the Atlantic. The story begins not with triumph, but with desperation. By late 1940, Britain was losing the Battle of the Atlantic. U-boats were sinking 300,000 tons of shipping monthly. The mathematics were brutal. Britain consumed more supplies than its shipyards could replace. Every week the gap widened. Every week starvation and defeat drew closer. The Royal Navy possessed hundreds of escort vessels, thousands of depth charges, and a success rate that barely reached 4%, 4 successful kills per 100 attacks. The problem wasn't courage. Escort crews were exhausted, spending weeks at sea in North Atlantic storms, hunting an enemy they could hear but not see. The problem was physics. A depth charge was a drum packed with 200 kilograms of amatol explosive, fitted with a hydrostatic pistol that detonated at a preset depth. Simple, reliable, fatally flawed. To drop depth charges, a destroyer had to pass directly over the submarine's estimated position. But the moment a warship passed overhead, it lost sonar contact. The submarine vanished from the ASDIC display. The escort commander had to guess. Where would the U-boat be in the 30 seconds between losing contact and weapons detonation? A submarine traveling at 4 knots covered 60 meters in that window. Crews routinely dropped patterns of 6 to 14 charges, hoping saturation would compensate for guesswork. It rarely did. U-boat commanders learned the rhythm. When the pinging stopped, the destroyer was making its run. Dive deeper, turn hard, count to 30. The ocean would heave with explosions, terrifying, destructive, and usually harmless. A depth charge had to detonate within 6 meters of a pressure hull to guarantee a kill. 6 meters. In the 3-dimensional expanse of the ocean, with a target that could be anywhere in a sphere 300 meters across, those odds were miserable. And even when charges detonated close enough to damage a U-boat, they often inflicted wounds the submarine could survive. Jammed diving planes, shattered gauges, traumatized crew. The U-boat would limp home, get repaired, and return to the hunting grounds. Lieutenant Commander Charles Goodeve understood this. A Canadian physicist working for Britain's Admiralty, Goodeve spent 1940 analyzing anti-submarine attack reports. The data was damning. Destroyers averaged 18 depth charge attacks per U-boat kill. 18 runs meant burning fuel, exhausting crews, and worst of all, leaving convoys undefended while the escorts chased individual submarines. The Germans exploited this ruthlessly. A single U-boat could draw off 3 escorts, leaving the convoy naked for the rest of the wolf pack. Goodeve's conclusion: depth charges weren't merely inefficient, they were operationally counterproductive. Britain needed a weapon that let escorts maintain sonar contact throughout the attack. A weapon that struck ahead of the ship, not astern. The British Army already had the answer, though they didn't know it. In the trenches of World War I, infantry faced a similar problem: how to hit enemy positions without exposing yourself to direct fire. The solution was the Stokes mortar, a simple tube that lobbed bombs in a high arc, clearing obstacles to strike targets you couldn't see. Goodeve proposed the same concept for submarines: mount multiple mortar spigots on a ship's bow. Each spigot would fire a contact-fused bomb ahead of the vessel in a shallow arc. The bombs would spread in an elliptical pattern, saturating the area where the submarine actually was, not where it had been. Contact fuses meant the bombs only exploded if they hit the submarine directly. Near misses simply sank to the bottom, inert. No explosions meant no confusion. If you heard a detonation, you'd scored a direct hit. The Directorate of Miscellaneous Weapons Development, yes, that was its real name, assigned the project to a team that included engineers from the Fairfield Shipbuilding Company. They faced immediate skepticism. Naval architects insisted that firing projectiles forward from a moving ship would create impossible ballistic problems. The ship's forward motion would add to the projectile's velocity in unpredictable ways. Wind, sea state, ship movement, the variables seemed insurmountable. The team solved it with mathematics and testing, lots of testing. They calculated that bombs fired at a 45-degree angle would clear the ship's bow and land in a concentrated pattern 200 to 250 meters ahead. The forward velocity would be consistent because the ship maintained steady speed during the attack. Sea state mattered less than expected. The bombs were heavy enough, 30 kilograms each, that wave action had minimal effect during their brief flight. The contact fuse presented a different challenge. Existing naval fuses were designed for torpedoes or mines, weapons that spent extended time in water. The Hedgehog bomb would be airborne for 2 seconds, underwater for perhaps 10 more. The fuse needed to arm in flight, withstand water impact without detonating, then fire reliably when striking steel at any angle. After months of development, the team produced a fuse that was elegant in its simplicity. A small propeller on the bomb's nose spun during flight, mechanically arming the firing pin. When the bomb struck a steel hull, inertia drove the pin into a percussion cap, triggering the 16-kilogram Torpex charge. Torpex was itself a recent development, 50% more powerful than TNT. A single Hedgehog bomb carried enough explosive to rupture a U-boat's pressure hull. 2 or 3 simultaneous hits meant instant catastrophe. The complete Hedgehog installation weighed just under 4 tons. 24 spigots arranged in 4 rows of 6, angled to create an elliptical impact pattern 40 meters wide by 36 meters long. Crucially, the weapon had no recoil in the conventional sense. Each spigot was a fixed steel rod. The bomb sat over the spigot with a tubular cavity in the bomb's base filled with cordite propellant. When fired electrically, the cordite exploded inside the bomb, not inside a gun barrel. The expanding gases drove the bomb upward while the spigot remained stationary. Newton's third law still applied. There was equal and opposite force, but it was distributed across the ship's entire bow structure, not concentrated in a gun breech. A destroyer could fire full salvos with no more stress than hitting a moderate wave. HMS Westcott received the first operational Hedgehog installation in December 1941. The crew regarded it with deep suspicion. Sailors are conservative about new weapons, especially ones that replace familiar systems. Depth charges were understood. You knew what they did, how to set them, when to drop them. This contraption of spigots and bombs looked fragile. The bombs themselves seemed too small to kill a submarine, and the concept, maintaining course directly toward a U-boat that might be firing torpedoes back, violated every instinct destroyer crews had developed. Attack runs were supposed to be aggressive, full speed, hard over the target, saturate the area. Hedgehog demanded patience, steady course, steady speed, trust the geometry. Westcott's first combat firing came on a January night in 1942, escorting convoy ON-55. The Aztec operator held a solid contact at 900 yards. The captain ordered the standard attack approach, then remembered they had the new weapon. He steadied the ship, called ranges to the anti-submarine officer. At 250 yards, fire! The salvo arced away, barely visible in the darkness. The crew waited. Nothing. The bombs sank without exploding, which meant they'd missed. But the submarine was still on the Aztec display, still clearly defined. The captain maneuvered for a second attack. Fire. This time 3 distinct explosions, sharp cracks utterly unlike the rolling boom of depth charges. The Aztec contact dissolved into a chaos of smaller echoes, breaking machinery, collapsing compartments, steel fragmenting under pressure. No U-boat surfaced, no survivors appeared. The ocean settled back to its usual patterns of wind and swell. Somewhere below, U-boat U-624 was flooding. Except it wasn't U-624. Post-war analysis revealed no U-boat losses matching that engagement. Westcott had probably hit a whale or a dense school of fish, or possibly a wreck. But the engagement proved the concept. Hedgehog could maintain contact throughout the attack. It gave immediate feedback. Explosions meant hits, silence meant miss. And the crew now understood the tactical advantage. They could make repeated attacks without losing the target. With depth charges, each attack run ended with the submarine disappearing into an acoustic nightmare of explosions and churning water. The escort had to wait for the ocean to calm, then search all over again, assuming the U-boat hadn't slipped away in the confusion. Hedgehog left the water clear. If you missed, you simply turned for another approach. The first confirmed kill came in March 1942. HMS Vanessa was escorting convoy QP-9 near Iceland when Aztec detected a submarine maneuvering into attack position. The escort commander, Lieutenant R.W. Keemer, ordered Hedgehog action. The salvo flew at 47 hours, 4 explosions. Oil and debris surfaced within minutes, followed by air bubbles that continued for 6 minutes, air bleeding from flooded compartments as the submarine settled to the bottom. U-432 was gone, 26 dead. The engagement had lasted 9 minutes from first contact to kill. A depth charge attack would have taken 30 minutes minimum, with no guarantee of success. Word spread through the U-boat force slowly at first. Commanders reported new attack patterns, escorts approaching head-on, maintaining course instead of circling. Then came survivor reports from U-boats, damaged severely enough to surface. Crews described impacts unlike depth charges, no warning pressure waves, no time to maneuver, just sudden hammer blows against the hull, followed by flooding. Kriegsmarine intelligence collected the accounts and struggled to make sense of them. The technical details seemed contradictory. Some survivors reported bombs raining from above. Others insisted the impacts came from forward. The explosions were small, too small for standard depth charges, but focused, localized, devastating. German engineers eventually concluded the British had developed some form of forward-throwing weapon, probably rocket-based. They were half right. The Admiralty had indeed developed rockets. The Squid system would come later. But Hedgehog wasn't rockets. It was simpler, more reliable, and already spreading through the escort fleet. By mid-1943, over 150 vessels carried the weapon. Production reached 30 installations monthly. The Americans liked the concept so much, they began manufacturing their own version, called Mousetrap, with 8 spigots instead of 24. It proved less effective. Fewer projectiles meant lower hit probability, but it was better than depth charges alone. The human cost of Hedgehog's effectiveness played out in steel cylinders beneath the Atlantic. Consider U-264, caught by HMS Wanderer in February 1943. The submarine was at periscope depth, preparing to attack convoy on 166. The first Hedgehog salvo missed. The commander, Captain Lieutenant Hartwig Lux, knew he'd been detected. Standard procedure: dive to 200 meters, run silent, wait for the destroyer to exhaust its depth charges, and leave. But the destroyer didn't leave. It circled back, regained contact, fired again. Second salvo, miss. Third salvo, 2 hits. The bombs struck aft, penetrating the pressure hull near the engine room. The explosions were compact but intense. Torpex was unforgiving. Steel plating that could withstand 15 atmospheres of external water pressure couldn't resist focused blast effects from inside. The hull ruptured along weld seams. Seawater entered at the speed of sound, driven by pressure differential. The aft compartments flooded before the watertight doors could be sealed. The submarine's stern dropped, angling the boat into a 40-degree dive. Lux ordered full rise on the diving planes, blow all forward ballast. It wasn't enough. The flooded aft compartments weighed tons. The submarine plunged past 250 meters, past 300. The remaining pressure hull began to groan, deep resonant sounds that every submariner feared. At 320 meters, something in the keel structure gave way. The boat broke in half. Both sections imploded within seconds. 53 men experienced what drowning at depth means: darkness, cold, pressure so extreme it crushes the rib cage before water fills the lungs. For most, unconsciousness came quickly, not quickly enough. The British didn't know any of this. Wanderer's ASDIC recorded the breakup sounds, heard the implosion signatures. The crew marked the location, dropped a wreath, and returned to the convoy. They'd done their job. Another U-boat that wouldn't sink another freighter. The mathematics of attrition were slowly, brutally, shifting in Britain's favor. But Hedgehog had limitations. The contact fuses meant the weapon only worked against submarines at relatively shallow depths, above 250 meters. Deeper than that, water pressure could trigger the fuse prematurely, or the impact with the seabed would waste the weapon. U-boat commanders learned to dive deep when under Hedgehog attack. Below 300 meters, they were relatively safe, at least from the bombs. The pressure hull wasn't safe. Type 7 U-boats were rated for 220 meters operational depth, with a theoretical crush depth around 280 meters. Going deeper was gambling with physics. Some boats made it. Others heard a single rivet pop, then the cascading failure as the entire pressure hull crumpled in microseconds. The Admiralty needed something for deep targets. The answer arrived in 1943. Squid! This was Hedgehog's bigger, nastier cousin. 3 mortar tubes mounted on the ship's deck, each firing a 200-kilogram bomb to ranges up to 400 meters. Squid used proximity fuses, depth-activated, designed to detonate at preset depths, whether they hit anything or not. This combined Hedgehog's ahead-throwing advantage with depth charges' ability to kill through near misses. A 3-bomb squid pattern formed a triangle 40 meters on each side. If the submarine was anywhere inside that triangle at the set depth, it died. The larger charges meant larger kill radius, 15 meters, double the depth charge effectiveness. HMS Loch Killen demonstrated Squid's capabilities in March 1945. U-1021 was running deep, 285 meters, believing itself safe from attack. Loch Killen's sonar tracked the submarine with new Type 147 equipment, the latest acoustic technology capable of holding contacts far deeper than older ASDICOM. The captain set Squid for 275 meters and fired. The bombs sailed in their high arc, splashed down in precise pattern, and sank. At 275 meters, all three detonated simultaneously. The U-boat was 11 meters from the nearest explosion. The blast wave hit like a solid wall. Pressure hull plating flexed inward, then rebounded, then flexed again as the second and third shock waves arrived. Welds cracked, piping fractured. The hull didn't rupture immediately, but the damage was catastrophic. Battery compartments flooded, releasing chlorine gas. Electrical systems failed. The diving planes jammed in the dive position. The commander had one choice: emergency surface. The boat broached in full view of the escort. Deck guns opened fire immediately. U-1021 settled by the stern and went down with all hands before anyone could abandon ship. By war's end, Hedgehog and Squid together accounted for over 70 U-boat kills. More than 10% of all German submarines lost to direct action. But the weapon's real impact exceeded simple kill numbers. They forced U-boats to operate differently. Commanders who once lingered near convoys, carefully setting up attacks, now had to attack quickly and withdraw. Staying in contact with a convoy meant accepting repeated Hedgehog attacks from escorts that never lost sonar contact. The psychological effect was severe. U-boat crews called it Zielsucher, target seeker. They believed incorrectly that Hedgehog bombs homed in on submarines acoustically. The truth was simpler and somehow worse. The bombs didn't need to home. They fell in such tight patterns that if the initial sonar bearing was accurate, hits were almost inevitable. German countermeasures were limited. U-boats began carrying bold, chemical canisters that released bubbles to create false sonar contacts. It worked against conventional ASDIC but was less effective against the improved sonar systems paired with Hedgehog. Some commanders tried crash diving the moment they detected escorts, hoping to get below effective Hedgehog depth before the attack developed. This often worked, but it meant aborting the attack on the convoy. Either way, the escort won. The submarine was either sunk or driven off. The cargo got through. The final evolution of a head-throwing weapons came too late for widespread use. Limbo, introduced in 1955, was a 3-barreled automatic mortar that could fire full salvos every 60 seconds. Each bomb weighed 180 kilograms. The system integrated with sonar to automatically calculate firing solutions. A submarine detected by a Limbo-equipped frigate had perhaps 90 seconds to escape before the first salvo arrived, then 60 seconds until the next one. Continuous pressure, no respite. But by 1955, the U-boat threat was history. Understanding what Hedgehog meant requires understanding what it replaced. In 1941, a destroyer hunting a U-boat burned through its entire depth charge magazine, 60 to 80 charges, for a 4% chance of a kill. Hedgehog installations carried 192 bombs ready to fire, with reloads possible at sea. Hit probability per salvo was roughly 12%, triple the depth charge rate. But because escorts maintained sonar contact, they could fire multiple salvos per engagement. 3 salvos meant a 33% kill probability, 4 salvos, 42%. The mathematics transformed anti-submarine warfare from a game of blind luck into something approaching a science. The men in the U-boats experienced this transformation as increasing dread. Early war patrols involved risk, certainly, but also periods of relative safety. Submerged, a U-boat was nearly invisible. Detection meant depth charge attacks that were frightening, but usually survivable. By 1944, detection increasingly meant death. The escort would approach steadily, calmly, and then bombs would arrive, sometimes hitting, sometimes missing, but always coming back. Again and again until either the submarine died or managed to break contact. Many U-boat commanders later said the waiting was worse than the explosions. Sitting in the dark, knowing the escort above still held contact, knowing the next salvo was coming, and being unable to do anything but hope the geometry would favor you this time. Some numbers clarify the impact. In 1942, U-boats sank 1,664 Allied ships, totaling 7.8 million tons. That same year, the Allies sank 87 U-boats. Exchange ratio, 19 Allied ships per U-boat. By 1944, with Hedgehog and improved radar and escort carriers all deployed, U-boats sank 132 Allied ships totaling 600,000 tons. The Allies sank 249 U-boats. Exchange ratio, 0.5 Allied ships per U-boat. The U-boat force had inverted from predator to prey. Admiral Karl Dönitz, commander of the U-boat force, understood this. His May 1943 decision to temporarily withdraw submarines from the North Atlantic wasn't surrender. It was acknowledgement that his crews were being slaughtered faster than they could be replaced. The withdrawal lasted only until new technologies could be deployed: snorkel breathing apparatus, improved torpedoes, Type 20 Wind submarines, with underwater speeds exceeding 20 knots. But the technologies arrived too late or in too few numbers. The Type 20 Wind program, which might have restored U-boat effectiveness, managed to commission exactly 4 boats before Germany collapsed. None saw combat. The cruel mathematics of Hedgehog extended beyond immediate kills. A U-boat damaged by near misses often limped back to base, only to be declared unfit for further service. Pressure hull damage was cumulative. A boat that survived one severe depth charging might crack apart during its next deep dive. Crews knew this. They knew every patrol decreased their chances. They knew the odds. And they went anyway because orders were orders and because submariners are a particular breed of stubborn. The weapon's simplicity was its genius. Hedgehog had no complex fire control systems, no delicate electronics, no temperamental mechanisms. Spigots, bombs, electric firing circuits, components that could be maintained by ship's crew without specialized training. When bombs failed to fire, it was usually a simple electrical fault or a dud propellant charge. Failures were rare enough that crews trusted the weapon. That trust mattered. Escort commanders would base tactical decisions on Hedgehog's reliability, knowing that when they pressed the firing button, 24 bombs would fly and the pattern would form exactly as calculated. Compare this to contemporary German weapons. The Type 7 U-boat carried 14 torpedoes, each costing more than a small house, each requiring careful maintenance and precise firing solutions. A spread of 4 torpedoes might take 5 minutes to set up considering target speed, range, angle, depth, and torpedoes failed, 30% dude rate in early war models. By contrast, a Hedgehog installation cost less than a single torpedo and could be operated by a single sailor with a firing key. Economic efficiency matched tactical efficiency. The post-war analysis conducted by Allied naval intelligence revealed patterns that validated Hedgehog's design. U-boats sunk by Hedgehog or Squid died, on average, 23 minutes after first contact. U-boats sunk by depth charges took an average of 97 minutes from contact to kill. Faster kills meant escorts spent less time away from convoys. Less time away meant better convoy protection. Better protection meant fewer merchant ships sunk. Fewer ships sunk meant more supplies reaching Britain. More supplies meant Britain stayed in the war. The chain of causation ran from a simple mortar bomb all the way to strategic victory. Yet for all its effectiveness, Hedgehog never captured popular imagination the way depth charges did. Films about submarine warfare invariably show depth charges tumbling from sterns, exploding in massive columns of white water. Dramatic, photogenic. Hedgehog lacked that visual drama. The bombs arced away almost gently. They entered the water with modest splashes. If they missed, nothing happened. If they hit, you heard sharp cracks and saw oil slicks, understated finale for such a lethal weapon. But submariners knew. In survivor interviews after the war, U-boat veterans mentioned Hedgehog with distinct unease. Depth charges you could evade. Hedgehog found you. The weapon's development spawned related technologies. The mousetrap system used on American destroyer escorts. The weapon Alpha used by the Soviet Navy. Post-war anti-submarine rockets like ASRO, all traced lineage back to the principle Hedgehog established. Strike ahead, maintain contact, use pattern fire to overwhelm evasion. Modern navies still use variations of the concept. The physics haven't changed. Submarines still need to be detected, tracked, and engaged before they can break contact. Ahead-throwing weapons still offer the best solution. Lieutenant Commander Goodeve's insight that maintaining sonar contact throughout an attack was paramount seems obvious in retrospect. But in 1940, with Britain losing the Atlantic battle, with conventional thinking dominating naval tactics, the ahead-throwing mortar was radical. It required escorts to approach submarines bow-on, the most vulnerable angle for torpedo attack. It required faith in mathematics and engineering over time-tested depth charge tactics. It required retraining thousands of sailors on new equipment while simultaneously fighting a desperate convoy war. That the Royal Navy accomplished all this while barely surviving speaks to institutional flexibility born of necessity. The U-boat crews on the receiving end had no such flexibility. They operated boats designed in the 1930s, using tactics developed in World War I, against weapons that belonged to a newer paradigm. Depth charges allowed evasion through maneuver and speed. Hedgehog negated both. The U-boat could run at 8 knots submerged for about an hour before batteries died. Hedgehog escorts could pursue at 15 knots indefinitely. The U-boat could dive to 220 meters. Hedgehog effective depth reached 240 meters with the right fuse settings. Every advantage submarines once enjoyed was being systematically erased by technology and tactics that rendered those advantages obsolete. The final tally was brutal. Of 162 U-boats commissioned during the war, 785 were lost to all causes. Roughly 30,000 U-boat crew died out of 40,000 who served, a 75% casualty rate, the highest of any military branch in the war. Hedgehog and Squid contributed directly to several hundred of those deaths. But the weapon's indirect contribution, forcing U-boats to withdraw from convoy lanes, disrupting attack patterns, creating psychological pressure, affected thousands more. U-boat commanders who survived the war consistently cited Allied anti-submarine weapons as more terrifying than aircraft, more deadly than escort numbers. The weapons that scared them most were the ones that gave no warning and no escape. Hedgehog, Squid, and depth charges fused for deep settings. In the end, the secret shell wasn't secret for long and wasn't technically a shell at all. But it accomplished exactly what its designers intended. It turned U-boats into flooded metal coffins, efficiently and at scale. The weapon didn't win the Battle of the Atlantic alone. That victory required radar, code-breaking, escort carriers, long-range aircraft, and massive industrial production. But Hedgehog was the tool that let individual escorts convert detections into kills with unprecedented effectiveness. It shifted the tactical balance just enough at just the right moment to help tip the strategic balance toward Allied victory. The ocean floor of the North Atlantic holds the evidence. 70-plus U-boat wrecks with distinctive impact craters from Hedgehog bombs, shattered pressure hulls, ruptured compartments. Steel coffins that were once machines of war, now monuments to engineering contests, where the margin between life and death measured 30 kilograms of torpex, arriving at precisely the right coordinates. The men inside those wrecks went to war in steel tubes, hunting merchant ships to starve an enemy nation. They died in those same tubes, hunted by weapons that ended the era when submarines ruled the deep.